Any question? All right. If you don't have any questions, let's continue. So last time we discussed about kinematics. And we said that for kinematic, you are not concerned about the forces. You are interested what is the velocity, what's the acceleration, and all of those things, what's the kinetic energy of the particle, and all of those kind of things. So we said that you have to describe the position of object as a vector r. And of course, vector r is changing the position from time to time. And you could have the option, you can put a Cartesian coordinate system with a unit vector ijk and describe that position r as xi plus yj plus zk, and simply go ahead and make a derivative of this expression with understanding that the only variable is x, y, z. I, j, k do not change with the time. So you can say the velocity is defined as change of position delta t as delta t goes to 0, and that becomes x dot I plus y dot j plus z dot k. If you are interested in acceleration, acceleration is defined how fast I change my velocity. So that's the definition of acceleration, delta v divided by delta t. And that becomes x double dot I, y double dot j, plus z double dot k. Now you can also go ahead use cylindrical coordinate system. And for cylindrical coordinate system, you have different set of coordinate system. For cylindrical coordinate system, you basically the same vector r is defined as er unit vector phi as a function of time, e theta, or let's call this one theta, e theta, and ez. So your unit vector is this time is different. Your unit vector is er, e theta, ez, but it's the same vector. It's the same vector. Same vector can be described in a cylindrical coordinate system by knowing the r, by knowing the theta, and by knowing the z, and then you basically produce that vector. So that vector is defined to come to here and you go up. That's a two vector. This vector plus this vector, it becomes r vector. So your r vector is r er plus z ez. That's your vector. Now if you are interested in the velocity, velocity again is defined a change of vector respect to time, position respect to time, and velocity is defined again as delta r delta t. So this time your er is changing. So next time your er is at different location, and so it is keep on changing, and therefore you cannot say der dt is equal to 0. You have to see what is that der dt here is. So we went to the calculation last time. I'm not going to repeat it again. And that how do you find that one? So, and we said that no matter what is a vector, you can say if your vector is changing the position, you can say is rotation times er. And that rotation is, for this problem, you have to use your right hand. That rotation is a theta dot k times er, or theta dot ez times er, and ez times ER is equal, you can see that your right-hand coordinate system EZ times ER is in the direction of E theta. Is normal to the plane of this Z and R. So that's one page. It's like a page of the book that you open it up. And so that is basically perpendicular to this page, like a page of the book. And that EZ times ER is in the direction of E theta. So you can go ahead and do this one. That becomes R dot ER, R theta dot E theta, and Z dot EZ. Your acceleration, again, is defined the same dv dt, same velocity, but in different coordinate system. And if you just go ahead and make another derivative of this one, that last time we showed that this becomes r double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta plus z double dot ez. So if an object is going around the circle, forget about the normal to the page, it's going around here, and that's a particle at any theta. So you can say that if r is a constant, the only velocity that you have is r theta dot, which is, you have seen it in your physics, they call it r omega, r omega. So your velocity is in this direction only is r theta dot, and let's say r is constant, so that becomes r theta dot or r omega that you have seen. And the theta dot is angular velocity, how the angle is changing, and that's called angular velocity, r omega or r theta dot. So that's a velocity, and velocity is tangent to the path because this is er and that's e theta, and the normal to the blackboard is called ez. Acceleration, if r is a constant, then you have acceleration is defined r double dot would be 0, r theta dot square. So you do have one acceleration in this direction, which is r theta dot square, and again r dot is 0, and you have r theta double dot. So you do have one acceleration in this direction, r theta double dot. So you do have two acceleration. Velocity, you have one velocity, but you have two acceleration. This is called tangential acceleration. Tangential acceleration. And this is called normal acceleration. We also went ahead, this is pretty much a review of the last time in the case that you didn't understand. And these two things we use quite a bit, and for some problem, make sure that if I said that something is rotating, r theta double dot, you remember that. And r theta dot square, you remember that. Or velocity is r theta dot, you remember that. And we mix it up with other coordinate system. We also defined angular velocity. We said that if you do have an object and that object rotate around this axis, again you use your right hand coordinate system, delta theta y, rotate around this one, delta theta z, rotate around here, delta theta x. You can think about it as if the system is rotating around this direction. And the change of this one respect to the time, how much is that one change respect to time, delta theta x, and respect to time, the change is called angular velocity. So your angular velocity is defined as theta dot x, the rate of change of this one respect to time, the rate of change of this one respect to time, the rate of change of this one. So you can say theta dot I, theta dot y, and theta dot z. Or you can say omega x, omega y, omega z. We can also define instantaneous of axis of rotation, instantaneous of axis of rotation. You have to find a point or a line that have all of the velocities equal 0. For example, if I have my book here and I'm rotating this page, all of this point have 0 velocity. They never go anywhere. So that is called instantaneous of axis of rotation. That they have, everything is rotating respect to this axis. You could have axis here, that's a rotation. It doesn't make any matter because the angle change. You can put here and say how much did my angle change. But if you want instantaneous of axis of rotation, all of them have to have a 0 velocity. Let's give you an example because this is also important. So let's say that you do have this bar, and you can say it's hinged here, hinged here. So this bar is rotate, and you can, again, let's use it goes up, and so you can say that this bar is going like this and have some angular velocity normal to the page, which is theta dot. Theta dot, and it has angular velocity theta, and delta theta respect to t is your angular velocity, which is normal to the page of the blackboard. If this is x, this is y, and that's z. So your angular velocity is normal to the blackboard, and doesn't make it. And you can say that this object is like this. Initially is horizontal. No, it is here. So again, doesn't make, and this angle doesn't make any difference. This angle, you can say that my object has rotated respect to this center, the theta. So the theta is the same. So still, your object has rotated around this axis, theta dot. So it doesn't make any difference. So with respect to this point, if you put a line here, and you put a line here, as if your object has rotated around this axis. So omega is the same. But that's not instantaneous of axis of rotation. Instantaneous of axis of rotation is this omega doesn't make any difference. This is the same. You put your coordinate system, you put the coordinate system, doesn't make any difference. As if the object has rotated. So if you put it here, as if your object has rotated, initially is here, no, it is initially horizontal, no, it has rotated the same amount. But if you would like to have instantaneous of axis of rotation, you have to make sure those points that, or those lines that you are talking about has 0 velocity. And in this case, this point is instantaneous of axis of rotation. So rotation doesn't make any matter. You can change the omega here, omega here, omega here, omega here. It's all of them normal to the page, and that is same omega. But if you want to have instantaneous of axis of rotation, the definition is that there are certain lines that all of those lines have the same, that have 0 velocity. 0 velocity. And the point have 0 velocity, the other point have velocity. So that's not instantaneous. So let's give you an example. Let's give you an example, then you will understand the concept of instantaneous. Let's say that you do have a cone, and that's my cone. A cone, and this angle is 2 alpha. 2 alpha. and the radius of this cone is r. The height of this cone is h. And this cone is rolling in the plane of the x and y with no slip. So it's going around the circle. So it is rotating around this axis. So it's rolling without a slip, rolling without a slip. I'm trying to find a garbage paper, so then I can show it to you something. You want to give me? That would be nice of you. I give it back to you. So this is a cone. Did you make a cone in your life when you were a little child? That's a cone. And this cone is rolling on the page like this. It goes all around, rolling without a slip here. And as a result, it has, thank you very much. As a result, it has some velocity, some omega here around itself, around its own axis. Let's call that is rolling like this, and it has omega here. And the whole cone, it goes around z-axis with capital omega. So if the cone is going with the capital omega, what is a small omega, which is rotating like this? What is a small omega? So it's like a tire of your car. Your tire is rotating and it goes all around the circle like this, and we are interested with the small omega. Of course, there are so many ways to solve this problem. There are not one way to solve this problem, but there are so many ways to solve this problem. So, and if you are clever enough, you can say, where is the instance, at this instance, when the cone is in the plane of the y and z, or is the bottom of the cone is in the plane of y and z, where is the instantaneous of axis of rotation? Where is the instantaneous of axis of rotation? You have omega, you have a total omega. You have to identify that total omega. Is there any line corresponding to that total omega that if that omega goes through that line, then it has all have zero velocity? It's like the previous problem. You have a lot of omega. Omega doesn't make any difference. So you have here, you can say my object has rotated respect to this axis. It's coming out of the page and it has rotated respect to this axis. That's still omega. Doesn't make any difference. Or you can say my object has rotated around this point that comes out of the page. No problem. Initially it was here. Now your object has rotated. But this axis that is coming, that doesn't mean they are in instantaneous axis rotation. You have to identify the axis or the normal to this case that they have all zero velocity. That's called instantaneous axis rotation. And in this particular case, the instantaneous axis of rotation is here. My student was doing the PhD of the ACL rupture, and we were wondering when we do the knee movement, different movement, how we can calculate the displacement. And one of the things that we were interested, where is the instantaneous of axis of rotation Because if we know the instantaneous axis rotation, then we can see what's the displacement at every other point, what's happening. So you have to find where is the actually as if a structure is rotating in respect to this axis, which has all zero velocity. It's like my here. That is instantaneous of axis of rotation. Every other point, the angle is the same, but this is a point that has no velocity. So you have to identify. So where is the, as I said, there are so many. Where is the instantaneous of axis of rotation for this cone? Can you tell me where is the instantaneous of axis rotation? This is a simple. You all can say, oh, this point has zero velocity. No matter how much is your hinge, it's coming out of the page. No problem. All of this point has zero velocity. How about this one? Rolling without sleep. Without sleep. Where is the instantaneous axis rotation? Somebody? What's that? Y-axis. Y-axis. Why y-axis? That's correct. All of this point that's in contact, as he said, is basically like peeling the banana. When you are trying to peel a banana, all of the points have zero velocity, and then they get separated. So the instantaneous of axis of rotation is here. In other words, your total omega vector, although it looks different, you do have this omega and you have this omega, but summation of these two vectors must be in this direction. So this vector, this omega vector, which is in this direction, and this omega vector, which is in this direction, if you add these two vectors, it has to be in this direction. Because this is as if in a standing, because all of the points around that line have zero velocity, as if you are just trying to separate atoms from the atoms. So for this problem, you can say my omega total is in J direction. And the same omega total is omega K minus omega, and this omega, cosine alpha J minus omega sine alpha K. So you decompose that omega, which is here, is rotating like this. Your thumb is going like this. You have to play in this course with your thumb. So it's very important, right-hand coordinate system, you use your thumb. So your system is rotating like this. And you can say my omega total is omega this. But I know my omega total must be in this direction, because that is instantaneous of axis of rotation. Or the direction of the total omega has to be in here, this direction. So from here, you can say the right-hand side must be equal left-hand side. So your omega total must be equal to minus omega cosine alpha. And you do not have K. That must be omega minus omega sine alpha. So from here, your small omega is capital omega divided by sine alpha. And omega total is equal to minus omega divided by tangent alpha. Now, we also defined another thing for you last time. we said if you have a vector, you have a vector A, and this vector A is rotating respect to some axis. So suppose it's rotating around this axis. So the vector A, as if is going around the cone. So if it's rotating around the cone. So you can think about it like this, and the vector A is going around the cone. So just because the A is a constant, that doesn't mean it does have no derivatives. And we said that last time we went through some procedure, and we said where is the A this time, where is the A next time. For example, next time A is here, and then we said what's the delta A, and then we find what is the derivative of A. And we said that for this case, if you are interested in the derivative of A respect to the t is defined as omega times vector A. Now for this cone that we have here, we just found it out what is a small omega here is, and we find a small omega. So your omega total vector is omega k minus a small omega, and you can say this a small omega, you can say is in this direction, then you can say that is in the direction of, let's say, this direction, we can call it ER. So you can say minus omega ER. And of course, at this instance, ER is, let's put the ER here, positive. And at this instance, ER is a cosine alpha j plus sine alpha k. So at this instant, at this time, ER is cosine alpha j plus sine alpha k. At other instances, different, because the cone is going different places. Cone is keep on rotating, and cone has different direction for ER. But at this instance, it is here. So if you are interested and we find out what is omega, we find a small omega, and we find a small omega is a capital omega divided by sine alpha. So you can put your omega total is omega k minus omega divided by sine alpha ER. Now, just because this is going with a constant velocity, and this is going with a constant velocity because the other omega is also constant, that doesn't mean you do not have angular acceleration. The next time your omega total is not here. Your omega total has gone to the different location. If this is a y and this is x, your next time your omega total in instantaneous axis here. Next time in instantaneous axis here. Next time in instantaneous. As if it is rotating, it is going to obtain, it still is in a plane of x and y, but there are different location. It's like as my hand is going around this table. So right now I'm here, next time I'm here, next time I'm here. So in instantaneous axis rotation, at this instant, in instantaneous axis rotation is this one. But that doesn't mean it stays the same place. As if rotating is going different. So therefore you can see, although the total omega has a constant value, but because it changed the direction, you do have angular acceleration. So, and in order to find that angular acceleration, you just go ahead and make a one more time derivative of this expression. And if you do one more time derivative of this expression, you can say omega dot total is equal, this is constant, no acceleration. This is constant, nothing. So only the ER is changing. So you can say is minus omega divided by sine alpha, and der dt and the omega that is responsible for change of this direction, no matter how much this cone rotates around its own axis, that ER doesn't change. The one that is responsible for the change of the direction of ER is this omega. That changed the direction of the ER. Not the cone, how much it rotates around itself. That doesn't make any difference. So this omega is not responsible for change of the direction of ER. The one that is responsible is this omega. So you can say, therefore, this one is omega k times ER. Omega times what we said, omega times A, and A in this time is ER. So therefore, from here, you can say the angular acceleration, omega dot total is equal to omega square sine alpha. And at this instance, K times ER is sine of this angle, which is a sine of pi over 2 minus alpha. This is 2 alpha, sine over 2 minus alpha. So is this vector times this vector, the value, times sine in between, and the direction is normal to the page that ER and Z. And that page is Y and Z. So in the direction of minus I. So your omega total acceleration is omega square sine alpha cosine alpha, and the direction of that one is I. So very important to understand in instantaneous of axis rotation that you have to identify, although all of the rotation is the same, doesn't make any difference, you identify one particular line that have all zero velocity. And once you identify that one, you may do. There are other ways to solve this problem, to find a small omega, but we leave it for the next problem that I'm going to solve for you. So in addition to this one, this coordinate, these are the two coordinates that usually we use. There is yet, let's solve another problem before we go to the next coordinate system. Let's solve another problem. So in the cylindrical coordinate system, we said that in the cylindrical coordinate system, we said velocity is r dot er, r theta dot e theta, and z dot ez. This is like your r omega. This is if r is changing. If r is not changing, like this, if it's going like this, then you have r dot. And it rotates here, then you have r omega, or r theta dot. And if it's going up, then you do have z dot as well. Acceleration is r double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta plus z double dot ez. All right, let's solve one more problem. Let's say that you do have, this is xyz. And let's say that you do have some spiral here, a spiral. It goes around z-axis, it goes up, and the radius of this spiral is capital R. And the angle of this spiral that's going is alpha. So you have your spiral, it's rotating like this, it's going like a spring. Just think about like a spring, and something is going around that spring up, and the angle of that spring is alpha. So that's your spring, a spring, like this. And this angle is alpha. All right? And the radius of this spring is r. So something is going around this spiral is going up with a constant velocity v0. So it's something is going up along that spiral with a constant velocity. So an object is going up with a constant velocity. Velocity, which we call it Vz, is equal to V0. The question is that what is the total velocity and what is acceleration? So what is the total velocity? What's a total velocity? And what is acceleration? Do I have what is the total velocity? So you can say no problem. This looks like a cylindrical coordinate system to me. This looks like a cylindrical coordinate system to me, and something is going up and is going up. It's like a cylindrical coordinate system to me. So you can say velocity is equal r dot er plus r theta dot is rotating, e theta plus z dot ez. So that's your total velocity. So it's going, something is going around the circle. It's like a spring. The radius of a spring is constant. It's going and it's going around that slope. So you can say that my velocity is equal to, I do not have r dot. My r never changes. At any location, if you look at the cross section, my r never changes. So my r never changes. And therefore I have simply r theta dot e theta plus z dot, which is v0 ez. The question is that what is a theta dot? What's a theta dot? The only thing that we are told that this is going with a constant velocity up, v0. So you can say no problem. At any instance is going in this direction. If it goes r theta here, it also jump up, and that's my spiral. So it's going up in this direction, and then at the same time it goes up, and that's my spiral. And this angle is alpha. This angle is alpha. So it's going around the circle, at the same time it goes up, and that's a path. That's a path that goes along this path. So it goes around the circle, and also it lifted up a little bit. So you can say no problem. Tangent alpha is equal to dz over r d theta, and this is d theta. Or your d theta that you are interested is equal to dz divided by r tangent alpha. From geometry. So therefore theta dot is, all of this thing is constant, simply z dot, which is v0 divided by r tangent. So the theta dot is simply dz dt divided by r tangent alpha, and that's equal to v0 divided by r tangent alpha. So I know I have my theta dot. I simply put it back in this equation, and I have my total velocity. So my total velocity is going to be equal to r, and theta dot is equal to v0 over r tangent alpha e theta plus v0 ez. That's my total velocity. And of course, this r and this r cancel. That's not a problem. If I want my acceleration, again, I have r double dot minus r theta dot square, er, 2r dot theta dot, r theta double dot e theta plus z double dot ez. Well, it is going with a constant velocity in z direction, so I do not have z double dot. My r is constant, I don't have any problem. So if I just go ahead and substitute back in this equation, r double dot is 0, so that becomes minus r theta dot square, er, r dot is 0, theta double dot is also 0. So because this is constant, so all of this term would be 0 and z double dot. So you just have acceleration, and that acceleration is in the r direction, which is basically on the page that you have. You have to identify circle that's going up. So it's going around this direction and it's going up, but the acceleration is in this direction. And that acceleration is equal to minus r. Theta dot square is v0 over r tangent alpha square, and the direction of er. So this is application of the cylindrical coordinate system that you can go ahead and do that. All right. Any question on this problem? Yes.
Could you please talk the theta dot again? How can I get the theta dot?
How did I find theta dot?
Yes.
Well, I said that if you go in this direction, r delta theta, then you go up dz, and that's a path of the spring. This is a path of a spring. You follow? So this is your spiral. You go around the circle and then you go up, and that's a path. That's this. And this angle is alpha. And from the geometry, you can say tangent alpha is equal to dz divided by r delta theta. That's what I said. Tangent alpha is equal to dz divided by r delta theta. If I'm going around the circle, at the same time I go up, then he said, okay, your path is here. So you went around the circle, you went up, that's the path. So your spiral is like this. You follow what I'm saying? All right. Did you understand? Clear? All right. So you went around the circle, then at the same time you went up. And that you went up is alpha. So how much you go around this direction, how much? It's like that you go around a slope. If you go around a slope, then you said, okay, that is my slope. That's a slope. I went in this direction and I went up this slope. Clear? All right. All right. So now you could have other coordinate system to use to describe the position of the object. I do not use in this course too much of that coordinate system, but we mentioned that. So, but generally we use mostly in this course cylindrical coordinate system and Cartesian coordinate system. And this equation that I wrote for you, we use quite a bit of this equation to make advantage of this cylindrical. Spherical, we don't use that much. But some problem you could have, and if an object is moving on a sphere surface, you may want to use a spherical coordinate system because your object is moving on the a sphere surface. So the people have used that one as a spherical surface, and we mentioned that one. But this is the last time I mentioned that a spherical, and you don't have to be too much worried about that one. But so for a spherical coordinate system, again, you have to have it a vector, same vector in the Cartesian coordinate system that we define, and also in the polar coordinate system that we define. Let's say x, y, z. And this is a vector. That's a vector that you are interested. And in order to get to this vector, what information we need is as if this is in a page of this is a page, as if this is on a page of the book that you open it up. So in order to say where is this vector, you have to know what is the length of the vector, r. What else do you need? You may have to say what is this angle, phi. That's like you open the page. What else I need? What else I need?
Angle between ZX.
You also need what?
Angle between.
This angle, right? Theta. So if I give you this three information, it's like you're opening this page of this book, and this is a book. I open it up, and then say, okay, my object is in this page. And in order to say where is in this page, that phi is identify the page. Where is that object in this page? You need r. And then you need another angle theta to say where is the object. So that's very important. I mean, you guys that sit in the class, you can see the demonstration. Online student, unfortunately, so I have to be a little bit more lenient to the online student because they do not see all of this demonstration that I do. So you need three. And again, you do have 3-unit vector. You have to define 3-unit vector. And your 3-unit vector is ER, another vector E theta, and another vector normal to this page, E phi. So ER and E theta is in the page that you open it up, and E phi is normal. So that's your 3-unit vector. So again, we are interested in this coordinate system, which is called a spherical coordinate system. What is the velocity, what is the acceleration, and so forth. And if you have been somehow monitoring how this page is open up and close, if you have monitoring of these pages, how it is closed and opens, then you do have what's the phi dot and phi double dot. If you know how is this r is changing in this page, then you have r dot and theta dot. And if you know the theta, then you can say how much is theta and theta double. So you can monitor all of those information. One time the page is here, one time the theta is this much, one time the r is this much, then I have the information. So you can basically go ahead. So now you have to say, what is the position of object? The position of object is defined as simply r, er. And somebody last time was asking me, oh, professor, how about theta and phi doesn't come to this picture? I said, no, that's RER. And the reason that it doesn't come to the picture, this ER is already a function of theta and phi. So you don't have to be worried about it. That's a vector. The length of the vector, unit vector. That's the length of vector. So you don't have to say, oh, how come this is not function of theta? No, it is function, but you don't see it. So now if you are interested in the velocity, and of course that you can say that this 3 vector ER times E theta is equal E phi. So that's normal to the page. ER, E theta, E phi. If you go in this direction, it's positive. If you go in this direction, negative. So that's basically your 3 vector. So now if you are interested in velocity in this coordinate system, is delta r divided by delta t. And that would be equal to r dot er plus r der dt. Now the question is what is this? The question is what is der dt? How do I find that? How do I find that? Der dt. How do I find that? And I have already mentioned.
Omega from omega.
Omega times what? ER. What's omega? What's omega? What's the omega vector? Omega times ER, you are absolutely correct. Whoever said that is absolutely correct. Good. Good students. So what's the omega? What's omega? Yes.
D dot E D plus theta dot E sub theta.
Your omega, you have 2 rotation. One rotation here, use your finger. Use your finger. One rotation is a phi dot in the direction of the z. That's a phi dot k. And you have one rotation theta dot in the direction of E phi. So you have 2 rotations. Your omega is actually phi dot in this direction, which is in this direction. We can call it k. K. Plus one rotation, theta dot, use your thumb, is perpendicular to the page of the this page that's open up. Just think about it as like this rotation. It is normal to that page. So whatever you have here, if something is rotating here, where is your thumb? Where is your thumb? Thumb is normal to the page. And that's theta dot and the direction of E phi. But the problem is that our coordinate system is ER, E theta, E phi. We don't have K. So now you have to just change the K to those unit vector. So you can say my K is really, this is my K, and the K is cosine theta ER. My K is cosine theta ER minus sine theta E theta. So you can say my omega is really phi dot cosine theta ER minus sine theta E theta plus theta dot E phi. Now you can put it back here, and you can do the simplification, and then you do have your velocity. And your velocity would have 3 components. You do have velocity in this direction, that's VR. You do have velocity in this direction, which is V theta. And you do have velocity normal to this page, V phi. You have 3 components of velocity. By putting back this information, R d ER dt, which is this is your omega. And then you have to multiply this one by ER. And then you do have DER dt. So the simplification of this one, I just showed you how to do that. You all knew that DER dt is omega times ER. But what's the omega? No problem. omega is one rotation here. That's a phi dot k. My thumb is going in the direction of z. One rotation here, which is in the direction of e phi. My thumb is going in the direction of e phi. You have to be able to play with your thumb. And these two rotations establish your omega. Then you say omega times ER, dER dt is that. But because we do not have k, you better write k in terms of ER, E theta, or E phi. And in this case, your k is cosine theta ER minus sine theta, and plus phi dot E phi that you have already here. And then that's omega times ER. You multiply this thing, and you put it back here, that you have total velocity. So in this coordinate system, your total velocity becomes, according to my notes, your total velocity becomes equal to r dot ER plus r phi dot E phi plus r theta dot sine phi E theta. Let me just make let's make sure that I put this one. Let me see. Okay, this is not correct, therefore, because my theta and phi is my note different. Let me just erase this one, so I know how to correct it. R dot ER plus R theta dot E theta, E theta, that's correct, plus R phi dot sine theta E phi. Does it make sense? Does it? You agree physically what is going on? If you are, you say, oh, is this make sense? If that's what he said, the velocity is equal. Physically, it makes sense, or it doesn't make sense. Well, you can say, well, I know definitely I have r dot. It's going in that direction, r dot. No, I have two more velocity. One is in this direction, which is simply is r theta dot E theta, and that's that. It's like r omega. So that makes sense also. So you have r dot and r theta dot. How about this term? Does it make sense too, or no? Why? Because this point, it is like this around, this is going around the circle. So just think about my page is going around the circle, and that is that. And this radius is r sine theta, and it is rotating with the phi dot. So that makes sense. That also makes sense. You do have three velocities. One is going around this like this. You have to always use it. So you have three velocity component. Well, definitely r is going here. Definitely it does like this. So that's r theta dot. Now, in addition, it goes around here like that. And you have to say, what is the radius of the base? Radius of the base is this one. Is radius of the cone. And the radius of the cone is r sine theta. And it's going with the phi dot. So therefore, it makes sense. Now, you can go ahead and do acceleration as well. And acceleration, you can also find acceleration. And acceleration becomes A is equal to r double dot minus r theta dot square minus r phi dot square sine square theta ER plus 2 r dot theta dot plus r theta double dot minus r phi dot square sine theta cosine theta E theta plus 2 r dot phi dot sine theta plus r phi double dot sine theta plus 2r theta dot phi dot cosine theta e phi. We have three terms. So you have to go ahead and do one more time derivative of this expression, and you know the omega, and then you can say no problem, I should be able to evaluate this one. That takes a little bit of time. I'm not going to do that. And we usually do not use cylindrical coordinate system that much in this course, but I just wanted to know yet there is another coordinate system that you can express. Any questions? The important thing was basically what's the omega, and you should be able to say what's omega. You do have three angles, and those angle changes, or you have two angle changes, and therefore that's theta dot and phi dot, and that's it. And you have to know what's the direction of those things, and not just theta dot. You have to say what's the direction, and the direction is in the direction of e phi, and the direction of that one in the direction of k. You have to use that rotation. All right. Now, so we identified three coordinate system for you, and we identify also angular velocity. We also discuss about instantaneous of axis of rotation. So those are important to understand. And we also said if the vector is changing, what's the derivative of that vector? Sometimes your problem is a little bit complex, and one coordinate system may not do enough thing for you. So, for example, your car is going with certain velocity, a certain acceleration, and it's rotating. Inside the car, you do have another object that is moving with respect to the car, and it's very hard to say what's the position of that object in the car with respect to the ground. So you have main reference frame, then you say where is the car at any time, and then inside the car there is another thing that is moving with respect to the car, and then you would like to know what's the velocity and acceleration of that object, because later on when we want to have forces, we have to know with respect to the ground, fixed reference frame. So therefore, and sometimes we have maybe 2 or 3 auxiliary coordinate system. So let's say that our main reference frame is here. Main reference frame, that's capital XYZ. Our main reference frame. Now, and this is the object, maybe car, and then you attach some auxiliary coordinate system. Auxiliary coordinate system respect to here. And then you do have an object that is inside this car, and this is your car, maybe car. Let's say car. And this is fixed to the car. This is fixed to the car. And then you do have something inside the car is moving. And that is, you can say, rho, at the distance rho. And this is rho respect to xyz, a small xyz. This is a car, which you have to say what's the position of the car at any time. That's the position of the car, capital R. And from here to here is a position of object. Let's say RO, and this we call it R. So this time we have one auxiliary. You have a car, and you attach one coordinate system to the car. And then you do have an object that is moving inside the car, which its distance respect to the car, or the chair of the car, or a seat of the car, is a rho. So this is called, this a small xyz is called auxiliary. So the question is that we would like to know what's the velocity and acceleration of that with respect to main reference frame. And suppose you have been monitoring the car. It's like a space shuttle. Where is the space shuttle? Where is the astronaut with respect to the space shuttle? And you have all of the information. And then we say respect to the ground, what is those astronaut is that? Not respect to the shuttle. We see the respect to the shuttle, they move around, they're hanging and free, and they just go around and no problem. And the shuttle itself is moving. Shuttle itself is moving around the orbit. And we can monitor from the ground, where is the shuttle? We do not have any idea what's inside happening, but we know the shuttle, where is the shuttle? But the people in the shuttle itself, they say, oh, I'm moving here, that my distance respect to the control computer is changing this much and that much, and then no problem. Am I clear? Am I clear? All right. So the question is that what is the velocity? We say no problem. We just have to go ahead and say velocity of the this point, well, let's call it P, point P. We have to say RP of particle, RP is equal to RO plus rho respect to a small xyz. That's all. This is the definition of the vector. The position of the particle respect to main reference frame is equal RO. Where is your auxiliary? Where is your auxiliary coordinate system? Which is, we call it here, O, plus rho small xyz. Now you simply have to go ahead and make a derivative of this expression. Find what is the velocity of the particle respect to main reference. So now you can say velocity of point P respect to main reference frame is equal to R dot O. R dot O means the velocity of the point O respect to the main reference frame, irrelevant of the particle. Where is the car? How is the velocity of the car? You can say x dot I plus y dot j plus z dot, or r dot I, r dot er plus r theta dot e theta and z dot ez. Cylindrical coordinate. Or you can use a spherical coordinate system. Doesn't make any difference. You have to use one coordinate system, and you have the information, you have x, y, z of the car. Forget about the particle inside. Forget about the particle inside. Just the car itself. I don't care whether there is an astronaut inside or there is no astronaut. What is that velocity? You pick up one coordinate system that you have, and you either cylindrical, spherical, Cartesian, you have. So that's R dot O, means the velocity of point O respect to x, y, z. Plus. Now you have to make a derivative of that vector, rho. Well, the derivative of that vector is velocity with respect to a small xyz, velocity of the point P respect to a small xyz, plus the vector rho. As a result, the car is being twisted. Even vector rho is constant, but if the vector rho is being twisted by the car, by rotation of the car, then you have to say it has additional velocity. It has additional velocity because rho is constant. It could tumble because this car could have angular velocity omega, and if the car is tumbling, even everything is frozen in the car, then it starts to tumble, and that has additional component, which is omega times rho. So, or omega times A that we said. So it's omega times rho xyz. So this is the main equation you have to understand, how to utilize this equation. And this omega is that whether your auxiliary reference frame is being twisted or not. If it is not twisted, then omega is equal to 0. So this omega is, you can say, whether auxiliary is rotating or not. You have to decide. If the car is not rotating and the bug is simply going inside, then you don't have this one. Then you don't have this term, because my auxiliary never rotates. My auxiliary is always the same, always maintain the direct. But if the car rotates, then say my car rotates, therefore auxiliary rotates too, because your auxiliary is attached to the car. But if the car never rotates, then you don't have omega. That's simply velocity at point O plus velocity of the object inside the car. That's your tubular. But if your car is rotate, that omega, even if the A rho is fixed, but the car is flipping, then you do have additional velocity, omega times A, that. Now, if you would like to have acceleration, then you say, no problem. I simply have to make one more time derivative of this expression, and then I have my acceleration. So you can say acceleration of point P respect to main reference frame is equal to acceleration of point O. What is the acceleration of the whatever coordinate system you use, x double dot I plus y double dot j plus z double dot, whatever you use for that point, you just simply put that information there. So that would be acceleration of point O respect to main reference frame plus, now you have to say what is the derivative of the VP respect to xyz. Well, it has respect to its own coordinate system, it has acceleration respect to axyz. But because the vector velocity of the v inside the car is flipping, that vector v is also has additional acceleration, which is omega times vxyz. Omega times vxyz. So it just have 2. Plus. Now, if your car has angular acceleration, then you have omega dot. So you have omega dot times rho xyz plus. Now you have to say omega times the derivative of that expression. What's the derivative of rho dot? What's the derivative of rho dot? We just mentioned that. Is a vxyz plus, but because rho itself is being twisted, it has additional thing, that's omega times rho xyz. So if you put all of this thing together, acceleration of point P respect to main reference frame becomes R double dot O, which we can call it R double dot O or acceleration of O, R double dot, this is R double dot O, or A, what is the coordinate of auxiliary or origin of auxiliary reference frame is accelerating, R double dot O, plus AXYZ, acceleration of point P respect to XYZ, plus, now if you just go ahead and simplify this expression, you have omega times Vxyz, you have omega times Vxyz, you have 2 omega times Vxyz Then you do have omega dot times rho xyz plus omega times omega times rho xyz. So you do have these two equations. Those two equations, it identifies the velocity dynamics, and you could have several auxiliary. Several auxiliary. You cannot. This is only one auxiliary. You could have several auxiliary. You have to start from the last one to the second one, and then to the first one to this until you get to the origin, and we will solve some problem. But mainly, you have to use these two equations. But you have to be clever how to use this equation. Very important. Let's solve one problem, then you will understand what I'm talking about. So let's recast it again. Sometimes we cannot describe position of something right away respect to ground. It will be too difficult. I mean, too difficult. You are in the car is flipping, something inside the car is going around. Very difficult. Maybe you can have two observers. One is sitting in the car and he constantly monitors what's going on. It's like a shuttle. Somebody is astronaut and constantly monitor what's going on inside the shuttle. Somebody from the ground monitor the shuttle itself. So having these two information, you put them together, some package, and you can be able to say what's the velocity and what's the acceleration of the point that you are interested. And these are all points. Later on, we go to the rigid body, but the same kind of thing, and we come with the equation that we need for the analysis. So you can say, no problem. We describe the position of object. What is my auxiliary is there. What is position respect to auxiliary? Respect to main reference frame is capital RP. And that is equal to this two summation of these two vectors. Your job is that you simply make a derivative. If you make a derivative of this one, that means velocity of your auxiliary coordinate system respect to main reference frame. If you make a derivative of this one, this has two terms. One is the velocity with respect to the shuttle, and because the shuttle is rotating, even this rho is constant, then shuttle has some additional velocity, which is omega times a, which in this case, omega times rho xyz. You have to understand where this term comes. If you are interested in acceleration, you simply have to make one more time derivative of this expression. Well, this term means acceleration of origin of the coordinate. This term has two components because it has one acceleration with respect to the car, but because that velocity is rotating with the shuttle, inside the astronaut has some velocity with respect to shuttle. But because shuttle is going around the orbit, then it has additional velocity. And that's omega times rho xyz, omega times that velocity. Omega times rho, but omega times a. And in this case, your a is a velocity. Here is omega dot, respect to the main reference frame. Rho, again, it has two components. Rho dot, which is vxyz, plus rho itself is being twisted. So that has additional component, omega times rho xyz. If you put them together, you come with these two equations. Let's solve one problem, you will understand. And then we solve much more complex problem. All right. Let's see whether I have some problem here, which is relatively nice. Okay. Any questions that you may have? Any question that you may have? All right. Let me see whether I have a simpler problem. I can certainly do this problem. But let's do one simple problem. then you will understand. This is a problem actually when I was a student like you, and my professor in MIT gave us. Okay? And so I don't have it here, but that's actually, if you come to my office, I show you my exams. So let's say that you do have a disk here with a radius r. With a radius r. Okay? And now we attach a blade here. We attach a blade here, and this blade makes an angle phi respect to the arm. Okay? And the length of this one is L. The length of this one is R. And this is a point that I'm interested, point P. Point P. And this is going with a constant velocity, omega. Is rotating with constant velocity, omega. And this arm is also, respect to this radius, is doing something here. So it's like that you have a disk here, you have something here, the disk is rotating, and the arm is doing something like this also. This was our problem in exam. And be honest with you, I made a mistake. I didn't get a perfect grade on this one. So we are interested, what is a velocity of point P respect to the main reference frame? And you can say respect to main reference frame, capital XYZ. XYZ is fixed, disk is rotating, and that is what we are interested in. So as you see, this problem is a little bit complex. This problem is not trivial, it's complex. And you may say, well, I like to solve it with the auxiliary coordinate system. Auxiliary coordinate system. So you can say, well, as if you are sitting in the top of the disk and you watch that arm. You are sitting in the top of the disk and you are watching the arm. It's like the astronaut in the shuttle. You are basically sit down and watch the other astronaut what they are doing. So you will attach some auxiliary reference frame to this system. Where do you attach your auxiliary coordinate system? Where do you attach to watch this arm? Where do you attach? Well, right here. Maybe here is I attach one auxiliary reference frame. I can call it a small xyz, a small xy. A small xy. And this point you can call it O, if you would like to say O. And this point we can call it maybe center, so you don't get confused with it. So now you can say, okay, no problem. No problem. This is my equation. Velocity at point P respect to main reference frame is equal to V dot O plus Vp respect to a small xyz plus omega times rho xyz. Okay? So velocity at point P respect to main reference frame, you just say forget about the arm, as if the arm is not there, auxiliary is not there, nothing is there. I simply erase this one so you don't get confused. Nothing is there. Here is nothing is there. What is the velocity of this point at this instance? The arm is not there, nothing is there. What's the velocity of this point? What's that? I cannot hear you.
Omega r.
Huh?
Omega
R theta dot. R theta dot. And the velocity is in this direction, R omega theta dot. And the direction you can say E theta, E, what you can call it, E theta 1. In this direction. E theta 1. So velocity of the point, and of course if you have all of the angle, if you know this angle at this instance, what is that? You should be able to theoretically say, let's say at this instance that this angle is a 30 degree or pi over 3. So you should be able to say what is the direction of that velocity. Forget about arm, and it has some velocity in this direction. And at this instance, or you can do it at any instance, doesn't make any, you can put as a function of theta, you can say at this instant theta is here, that's a velocity at this instant. So velocity of that one is r omega, and the direction of is E theta 1. And you should be able to say what's the direction of that one at any instance. If the next time this point is here, the velocity is in this direction. If the next time is here, then this point velocity is in this direction. So you should be able to say velocity at any time was that direction here is. For example, this is like your physics in high school. You shouldn't come to this class and say, what's the velocity at point O? If you have a problem, then maybe this is not the class for you. Be honest with you. If you do not know that's r omega or r theta dot, which I have already described, you may want to think twice whether this is a proper class for you. But if you know that, then you're okay. And if you work hard, that's fine. So we have this point. Now you go ahead, and this is a auxiliary. That's a small xyz that is attached to the disk. Attached to the disk. No, you just forget about the disk itself. You forget about the disk itself, as if the disk doesn't exist. Disk doesn't exist. Disk doesn't exist. And this object is going around with this angle phi. And what is the velocity of that point? What is the velocity of that point? What is that? L phi dot. L phi dot. The length is L. The angular velocity is phi dot. And the direction of that one is in this direction, E phi 1. E phi. E phi. E phi. That is the direction of that velocity. And if you know the phi and you know all of those things, you should be able to say what's the direction of that one. So velocity of point P respect to a small xyz is equal to L phi dot direction E phi. E phi. Is 3:15. Time goes 3:15. 5 more minutes. So that take care of that one. No, you said what is omega times rho. So this, my auxiliary reference frame is here. That's my auxiliary reference frame, a small xy. And this auxiliary reference frame is being twisted. It's being twisted. It goes around. This auxiliary reference frame is being twisted. As the disk is rotating, my auxiliary reference frame is twisted. And that one, as a result of twisting, it keep on changing my auxiliary reference location. So now you can say, okay, now I have omega of my how much my auxiliary reference frame is being twisted, and omega is that one. That's big omega. That's my auxiliary reference. So you can say omega times rho xyz is equal to omega, and that vector you can say omega is coming out of the page. You can say omega k. You can say omega k, and k is coming out of the page. Is in this direction. K is coming out of the k is in this direction. is coming out of the blackboard, x, y, z, like this one, perpendicular to the board. And that's omega. And I said omega doesn't make any matter whether here, you here, direction is important. Times rho x, y, z, and now rho respect to this one is this vector rho, and the direction of is ER, let's say ER1. And that's L ER1. So what is a K times LER1? What is a K times ER1? What is a K times ER1? That's right, E phi. That's E phi. K is here, is exactly E phi. So this is omega times L E phi. So your total velocity is going to be equal to R omega E theta 1, which E theta 1, we just mentioned that. What's E theta 1? E theta 1. So E theta 1 is in this direction. E theta 1. We have one velocity here, R omega E theta 1. We do have two component velocity in this direction, normal to this one, and another component velocity. And that component velocity is L phi dot plus L omega E phi. So you don't have two component velocity, one velocity here, one velocity here, you add them up. You add them up. So why don't we stop here and we continue on this auxiliary. We solve few more problems. You have to become very comfortable with auxiliary, and very important. And we solve some problem they gave in exam. Hopefully you can see what kind of problem you should expect. But you go with this equation and you go with this, but may understand what is going on. It's very important in dynamic. You have to understand what is going on, and then you will be fine. All right, we see you on Friday.